Hello and welcome. As you may recall, a couple videos ago we introduced some code that tours all the modes of the 6847 T1, which is the updated VDG for newer model Coco 2s. One of the things the code does is it responds to a few different kinds of keystrokes. It'll pay attention to L for lowercase, R for reverse, B for border color, and any other key would advance to the next mode. We did not talk about how the code did it. I chose to do something kinda cute and fancy. Why did I do it that way? What way did I do it? That's all coming up. To see how the keyboard code fits in, we're just going to take a look at main first. So main is divided into a couple sections. First we have all the initialization, and then we have our loop. And the loop has a couple places where we might branch up. So the main loop, this label, we branch up to here whenever we've gone to a new display mode or we've toggled between the name screen and the display mode screen. And so the only real difference between branching up here and branching up here is we will activate the new display mode we're supposed to show. The label over here controls the loop where we just byte by byte, or I should say word by word, fill in garbage into the screen. We check if we're done, and if so, we wrap around to the beginning. You'll notice we are doing a plus 256 because the first 256 bytes are reserved for bytes 0 to 255. Rather than having everything be garbage, we start the garbage 256 bytes later. Once we know that U is in range, we go ahead and get our bytes, we store them onto the screen, and then here is where we take a look at the keystrokes. So rather than having all of the keyboard logic inline inside main, it's now separated into its own routine. And then we handle the branching. You'll notice that we're assuming that when ProcessKeystroke is called, if there were no keystroke, then the Z condition code will be set, just like Polecat does. When there's no keyboard set, we just continue filling up the screen rather than needing to show the next display mode. But if there was a keystroke, then we'll go ahead and show the display mode. So what does ProcessKeystroke do? Of course it will call Polecat, and if Polecat has nothing to say, we just return, and then the Z condition code has already been set for us. If keyboard input is detected, then we actually look through an array of structures to tell us what to do. So the main difference in how this is working now is it's data-driven rather than code-driven. So anytime we want to add a new keystroke and a new handler, we can simply add a new entry into this array. Let's take a look at that array. ProcessKeystroke infos is an array of ProcessKeystroke info structs, and each struct only has two fields. First is the character we're comparing with, and second is the routine that we want to jump to. So whatever this is, let's say it's L, then the routine would be the routine to handle lowercase, for example. So if you take a look at the array, it's pretty simple. N means we would want to go to ProcessKeystroke N. L means we would want to jump to ProcessKeystroke L, and so on. And then the very last entry, we use 0 to indicate that's else or other. Basically, any keystroke that we haven't matched yet would match to this, and then we would jump to this routine, ProcessKeystroke other. The advantage of doing things this way is if later I decide, oh, you know, I would like to add a new keystroke, I can just modify this array, add my new routine, and I'm good. The other advantage is it's fun this way. I just wanted to do something a little more extensible. Pretty much all the videos that you see on my channel are just stuff that I thought would be fun to do. So that's how this fits in. And the final advantage is I could, in theory, reuse all of this stuff if I wanted to make a brand new app that might need to respond to a bunch of keystrokes. I could simply make another version of this array, but I could keep, in theory, the routine that you just saw that handled this the same. So let's take a closer look at that routine again. We'll go back. Once we know there has been keyboard input detected, then we're going to cycle through that list of process keystroke info structs. So we start at the beginning, and we check to see if we're at that 0 entry, that last else other entry. If so, that means we've reached the end and nothing is matched, so go ahead and do that routine. So goToRoutine will handle that. goToRoutine does an indirect JSR, so it will jump to the subroutine that is pointed to right here at the routine address. After that returns, we need to make sure we zero out the Z condition code flag so that our caller realizes we have had a keystroke. Coming back up here, after we check to see if we're at the other one, if we're not, the next thing we do is we ask whether A, which is the register that polecat will fill out for us, matches the keystroke on the keystroke info that we're looking at. And if so, we go to that routine. Finally, we didn't have a match and we weren't at the last one, so we'll just advance X to the next one, and we loop back up to the top. Are there any disadvantages to this approach? Should we just always do this approach? It's extensible, it's reusable, and it's fun. Why wouldn't we just always do this? Well, I can think of one reason. All these routines we have to go to, we're now doing an indirect JSR. So first of all, the fact that it's a JSR means this is not going to be relocatable code. I'm not going to really say much more about that, but it's definitely an issue if you ever want your code to be easily relocatable. Perhaps the bigger issue is that we're going to be incurring quite a cost in terms of cycles. So what do these little routines look like that we keep JSRing to for each keystroke? They're these tiny little routines. Every time we go to them, we're doing, first of all, a subroutine jump, whether it's a J or a B or whatever. It's a subroutine, so we're pushing the stack location, we're doing whatever we need to do, and then we're doing a return, which will then pull the program counter off of the stack. That's what they all look like. The other, by the way, is a little bit bigger. This is code that we had way back before we were doing any T1 code. This simply advances the VDG disp mode pointer to the next one. It just advances forward so that this variable stays updated. Because when you hit a keystroke other than L, R, B, or N, that means you want to go to the next display mode. But again, RTS at the bottom here. We didn't used to have this. So we're adding some cycles. We're adding some cycles to go to subroutines. We're adding some cycles to do a JSR rather than a BSR. And we're adding cycles to do a subroutine at all, as opposed to just doing a branch. The older code, it might not have been beautiful and cute and fancy and extensible and reusable, but it was pretty efficient. We were just branching wherever we needed to go to, and we were using nice, simple, relative branches. What is the cost of doing stuff this way? We can use lwasm to count the number of cycles each instruction is going to cost, and there are a couple ways to do that. This way is just right on the command line. It'll just do it for the whole thing. Turning on the cycle count is considered a pragma, so you would just say -- pragma equals, and then CD is the code for I want to be counting the cycles. And it will also break it down based on the cycles, the base cycles, and the addressing mode. That's what this CD will do. So let's run that and take a look. I'm going to jump over to a JSR to get an idea of how expensive they are, and actually brings me right into my ProcessKeystroke routine. So a JSR to polecat using this indirect mode is going to cost me 7 as the base number of cycles plus another 5 because of this addressing mode. 12 is a lot of cycles. If you compare it with like a simple branch, that's 3. 12 is a lot more than 3, but it gets worse than that. Let's take a look at what happens when we JSR using the routine address that's in the array of structs. 7 plus 7, that's 14. It's a little bit worse, 14 compared with 3. Let's also take a look at the number of bytes that are used. So for the JSR, we're using 1, 2, 3, 4 bytes. For a relative branch, we're using 2. So the difference is not quite as dramatic in terms of number of bytes, but it's still pretty clear that we're definitely paying a price to do the JSR. So the cost is pretty clear, but we still have to ask ourselves, how much do we care? If you think about how often this is going to happen, the only time that we're using this JSR is if we actually found a keystroke. So if there is no keystroke, we're going to immediately return from this method. It's only when the user is actually hitting a key that we're going to incur the cost. And what I think is a pretty decent rule of thumb is, compared to when the user is not doing something happens almost never. Pressing a key on the keyboard, hitting a button on the joystick, this just does not happen very often compared to the processing speed of the CPU. How many times through the loop that calls this will there be no key pressed? I would say the vast majority. Even if we were coding up a word processor program where we expect the user to be hitting keys a lot, most of the time will be spent in between keystrokes. But there's another cost, not as great, but still it happens a lot more often. And that is just this stinking return and the branch to subroutine to get here in the first place. That does happen all the time. So in main, every single time through the loop, we always call this to check. And so we have added a BSR and an RTS just for the luxury of compartmentalizing this into its own routine. How much is the BSR to process keystroke costing us? 7 cycles. How much is the return costing us? 5. So that's now 12 cycles every single time through the loop, just because I moved this into its own routine. Now what I could do is I could keep all this stuff, but not have it in a separate routine. I could just inline that inside main. Then I would kind of have the best of both worlds. I would have my extensible code that's all fancy, but at the same time I'm also not doing those extra 12 cycles every single time through the loop. So that's just a trade-off. And also, this app just doesn't have to be that fast. Like anything, it's a trade-off, and depending on your application, you might want to go a different way. Even in this application, you might have a different opinion from me and want to go a different way. But the way I did it was kind of fun, and it works pretty well. I can hit the keyboard a lot, and it's pretty responsive. Anyway, I hope you enjoyed it, and I will see you next time.